Anticyclonic gloom. What is it? Why does it happen at this time of year? And how long will it last? I'm going to try and answer those questions in this week's Met Office Deep Dive, including an explanation of the weather pattern we've got at the moment and why it would give us warm sunshine in the summer rather than dreary cloud in November. And I'll try and explain the Foehn effect. All that to come, but before I get started, in last week's Deep Dive, I promised that this week, if you tune in, I would have a special announcement. So without further ado, take a look at this.
Head between your knees like that.
Try and touch as little of the ground as possible, basically. Stop laughing. That's a demonstration, live demonstration on YouTube.
Yes, the Met Office Weather Studio Live is coming back this Friday, the 8th of November at 12:15. Now, those of you who aren't aware, we used to do these regular Tuesday lives. 2020 and before, and we're bringing them back. They're similar to the Deep Dive, but the main difference is that they will be live. So if you tune in at 12:15 on a Friday, it will be your opportunity to ask us questions. We won't necessarily be coming up with the topics ourselves like we do in the Deep Dive. So please hit subscribe if you're following us on YouTube, and you won't miss one of those when they pop up in your feed. Now, we've had this high-pressure system with us for just over a week now, and it's brought mostly grey skies across the UK and some drizzle. It's not brought entirely dry and sunny weather, and that's primarily because of the time of year, and I'm going to be explaining why that's the case in just a moment. But before I do, just in case you're about to head out to a bonfire display, I thought I'd give you a quick rundown of conditions on Tuesday nights. And because of the high pressure, well, we're not expecting anything particularly unsettled, nothing particularly wet or windy, so mostly fine for bonfire night and plenty of dry weather, although there will again be some drizzle, most notably southwest Scotland, northwest England, parts of West Wales and Northern Ireland. That's where we've got this southerly wind coming through, and a lot of low cloud pushed against these hills and coasts in the west, giving some drizzle. The brighter whites here show areas of hill fog, and if we do get some cloud breaks during the day into the evening, well, those clearer spells will get filled in by fog as well, and that will be helped along by, of course, the bonfire smoke in the atmosphere. So all in all, a gloomy but mostly settled bonfire night, and into the start of Wednesday there's likely to be, as a result of the gloom, widespread fog across many parts of the UK, particularly towards the south where winds are generally light. Poor visibility first thing, so watch out if you're on the roads during Wednesday morning. Some of that fog, I suspect, could last all day. The sun is particularly weak at the moment. But it's a mild start to the day. These are the kinds of temperatures at 11 a.m, so generally double figures, whether you've got the cloud or some sunny skies that will be a little more prevalent across northern Scotland. And to explain why it's mild and to explain why we're most likely to see clear skies towards the north of the UK, northern Scotland in particular, let's take a look at the bigger picture. Now, at the moment, the UK is sitting in between low pressure in the Atlantic and higher pressure over the continent. That higher pressure is just edging a little further east over the next few days, and that allows this southerly airflow, particularly for northern and western parts of the UK. Now, as I mentioned, if this was in the summer, we'd be experiencing very, very different conditions. You see the warm colours on the map there. We've got a southerly wind, we've got high pressure in place, all the ingredients there, if this was August, for some very warm and sunny weather. So why isn't that the case at the start of November? The primary reason is the sun is weak, and these colours represent the temperature at 5,000 feet. The reason we use the temperatures at 5,000 feet in that kind of map is to show air masses, areas of similar weather characteristics, and of course where you've got a stark difference between different air masses, you get weather fronts and you get bands of rain or snow and so on. This again is showing the temperature at 5,000 feet or 1,500 metres, and typically, certainly in the summer, it correlates very well with the kinds of weather that we experience at the surface. And that's still the case for some parts of the globe. So if we look at Africa, we've got the very warm or hot colours there. And if I switch to the surface temperature, very warm or hot weather over Africa at the moment, indicated by temperatures in the mid to high 30s. Those are the surface temperatures. Just clicking onto the 5,000 feet temperatures or 1,500 metres, and the temperature at that height is in the low 20s. The temperature at the surface is in the mid 30s, and so there's a difference there of about 10 to 15 degrees. The temperature typically decreases with height, and that typically decreases at a rate of about a degree every 100 metres. So if that was in a perfect scenario where the temperature decreased uniformly with height from the surface up to 1,500 metres, you'd expect it to be 15 degrees colder at 1,500 metres. And that's roughly the case for, say, West Africa there. But it's not the case for parts of Europe. Now, this is the surface temperature again. You can see some quite cold air there across central parts of Europe. Temperatures in the mid single figures or so. I'm going to skip forward to Wednesday, actually. Wednesday shows it even more clearly. This is 5 o'clock on Wednesday. Temperatures in the low to mid single figures across Central Europe. But putting the temperature at 1,500 metres on, and it's actually higher. 10 degrees, 8 degrees, 7 degrees, as you can see. And it's the same for the UK. So this is the temperature at 1,500 metres, Wednesday afternoon, 8 to 11 degrees. The temperature at the surface, 5 degrees, 9 degrees, 14 there over Ireland. So in many places across Europe at the moment, the temperature at 1,500 metres is actually higher than the temperature at the surface. And that's because we've got high pressure in charge, and higher pressure in the winter half of the year often leads to colder air at the surface than at 1,500 metres. And that's because the nights are much longer than the days, and under higher pressure you get a longer period of cooling during the night, and a shorter period of warming during the day. The opposite happens in the summer. In this situation in the summer, the temperatures would be rising considerably during the day, not cooling too much during the night. And just to illustrate this, I've got what we call a tephigram. Tephigram simply stands for temperature, that's the T. Phi, that means energy or entropy, and it's a gram, so it's a diagram. And a tephigram is a diagram that shows the temperature and the energy of the atmosphere as you go up through it vertically. And this is an actual reading from a weather balloon that was sent up from Albemarle in northern England midnight last night. And I appreciate it might be difficult to see it, but there is a thin red line that goes up through the top there, and it corresponds to a cooling. The temperature there is on the x-axis. There's -50 where I'm pointing there, -100 over here, and then the height is going up on the y-axis here, all the way up to 13 kilometres at the top. And a couple of things to point out here. Mostly the temperature is decreasing with height. So as you get higher in the atmosphere, the temperature's going down. That's the red line, remember. But there's a point up here where the temperature increases with height. And that is the top of the troposphere. The troposphere is that part of the atmosphere where most of our weather takes place. and the troposphere is marked by, on average, the temperature decreasing with height. And the reason is because you get the sun warming the land or the sea below. That warmth rises and cools through the atmosphere, and this continuous cooling, on average, takes place up to this point, which is the top of the troposphere. Then it starts to rise, and the reason it starts to rise as it goes into the stratosphere is because in the stratosphere, you've got something taking place called photolysis, where the sun breaks apart molecules of ozone, and that causes a reaction. It causes a release of heat. And so in the stratosphere, the higher you go, the warmer it gets again. But the air is really thin in the stratosphere. The pressure, remember, goes down as you go higher up in the atmosphere because you've got less air coming down on top of you. And so it probably doesn't feel that warm even if temperatures are rising. This, by the way, is something like -60 up here at the top of the troposphere. Anyway, there's another bit way down here where also you've got the red line increasing rather than decreasing with height. And it's quite a sudden increase over just a matter of tens of feet, really, or tens of meters. And it suddenly goes up to about 13, 14 degrees. So it drops away from the surface up to, I think, about 1,000 meters, so a kilometer above us, and then the temperature rises, and that's called an inversion. It's more clearly seen if we skip to the next image, which is the same weather balloon reading, but all that's happened going from this one to this one is that it's been tilted. This is often called a skew-T diagram. It's skewed. So now the temperature lines are at 45 degrees essentially. So -20 here, and then that isotherm, that line of equal temperature, goes up this way rather than up straight vertically. So -20 is here, and it points to that bit there on the line. And you can see this is the point at which the stratosphere begins, and you can follow that line down here, and it's about -60 degrees. The other thing to point out on this is the blue line, and that's the dew point temperature. So it takes readings of the wind and the pressure and so on, but it also takes a reading, as well as the air temperature, the dew point temperature. The dew point temperature is the temperature at which the air must cool to become saturated. If the air temperature and the dew point temperature are the same, you get fog if you're at the surface, or higher up, you get cloud forming. So where these lines, the red and the blue, are close together, you get cloud, and where they're far apart, you get very little cloud, you get very dry air. And you can see at higher altitudes, the blue line goes quite far to the left, and there's this big gap. That indicates very dry air, no cloud if you were flying through it. Some cloud, perhaps at this kind of height up here, that's probably about, let's see, 3,000 to 5,000 meters high. But towards the surface, the two lines meet. And let's zoom in on that bit, because this is the bit we're interested in. This slice of atmosphere here, the two lines are touching, and that means there's this layer of cloud that goes from about 700 meters up to that inversion that I mentioned at 1,000 meters. So there's this layer, what we call stratus, 700 meters up to about 1,000 meters, marked out by the two lines touching. And the air cools at a slower rate where you've got that cloud. There's two different rates in which the air can cool, and this is significant for the Foehn effect. This will come clear in a moment. There's something called the dry adiabatic lapse rate. Lapse rate means the rate at which the temperature cools, or lapses with height. Adiabatic basically means you take a parcel of air, lift it into the atmosphere, and it warms up or cools down only because it's encountering air with lower pressure or higher pressure, and that's what causes it to warm up or cool down. Adiabatic basically means there's no added heat except for the fact that the pressure is changing as the air is rising. So when you take air from the surface and lift it through the atmosphere, it encounters lower pressure. That means that the air parcel expands and the molecules have got more space to basically fly about in, and so they slow down and the air cools. Likewise, if the air descends through the atmosphere, it compresses and gets warmer. The same thing happens when you pump up your bike tyres. When you pump up your bike tyres, then the pump, or at least the inlet valve, gets really hot because you're compressing that air, you're adding pressure, and that increases the temperature. So, rising air through the atmosphere, lower pressure, lower temperature. And the rate at which that happens is, as I mentioned before, 1 degree roughly per 100 metres. That's the dry adiabatic lapse rate. That's the rate at which the temperature decreases for dry air, air that isn't saturated, air that isn't in a cloud, basically. But at the same time, you've got the dew point that starts off on the surface at a certain value, and that also decreases, but at a slower rate. So that decreases at about 2 degrees per kilometre, as opposed to 10 degrees per kilometre. So at some point, the air temperature decreases enough so that it meets the dew point temperature at a certain height. And you can figure out the base of the cloud by doing that kind of calculation. And in this case, you've got the air temperature decreasing 1 degree per 100 metres, and then at this point, it meets the dew point temperature, a cloud forms. Then it decreases in temperature at a slower rate, and the reason is because it's saturated, and so in order to continue decreasing, then it must release water vapour, and that's because lower temperature air contains less water vapour. So as it continues to cool, as it rises through the atmosphere, it must release water vapour. That's called condensation. Basically, that's why you get a cloud. The water vapour turns to water droplets. But that, at the same time, releases energy. It's called latent heat energy. And so that release of energy means that you've got energy added, and it slows the rate of cooling. That's called the saturated adiabatic lapse rate. And that cools at a rate of 5 degrees per kilometre. So it's about half. And it cools at an even slower rate, even higher in the atmosphere, because you've got even less water, or cools at a faster rate, I should say, higher up in the atmosphere because you've got less water vapour. But the important thing to remember is when the air is dry, it cools at a rate of 10 degrees per kilometre. When it's saturated, when you've got clouds, they cool at a rate of 5 degrees per kilometre. Why is that important? Well, let's take a look at the situation across the UK Wednesday afternoon, because it's quite an interesting one. What we've got is this marked contrast across Scotland. Zooming right in, and just want to highlight 3 areas here. Stirling, Braemar, Lossiemouth. Lots of cloud over the Highlands and Grampians here, and some blue spots there as well, giving some drizzle. A lot of low cloud, the brighter whites indicating hill fog as well. So Stirling's cloudy, mostly dry. Then Braemar, fairly foggy, some drizzle about. Lossiemouth, no clouds whatsoever. And this is because of the difference in the dry adiabatic lapse rate, the saturated adiabatic lapse rate, and the progression of the air over the hills leading to a Foehn effect. What on earth am I talking about? Let's draw a diagram to try and explain. This is how the Foehn effect works. Okay, so we've got the surface of the ground here. This is sea level. And then I'm going to draw the y-axis up here. This is the height. That's 1,500 metres, 1,000 metres, 500, and 0. And then imagine there's a mountain range across Scotland, for example, that goes up to about 500 metres. Fairly modest when you consider other mountain ranges around the world. Obviously, there are higher mountains in Scotland, but there are large parts of central Scotland, the Highlands and the Grampians, that are around 500 metres. So imagine that's the case. It makes it easier for calculations as well. So that's the mountain range there. At the same time, there's an inversion, as there is with the current weather situation. There's this inversion at 1,000 metres, and above that inversion, you've got this high pressure, so the air is slowly sinking, slowly descending, and the air up here is dry and it's warm, it's 10 degrees. At the surface, before the air goes over the mountain, so the temperature might be 10 degrees and the dew point might be 8 degrees. Then the air is pushed over the mountain, it's forced to rise. So it starts to climb. Just taking into account the air temperature, if that went all the way up to 500 degrees, it would cool by 5 degrees. So it would be 5 degrees at 500 metres. The dew point would cool by 1 degree, so that would be 7. So we've got 5 and 7. But you can't have the air temperature being lower than the dew point. At some point, they're meeting, and that looks to be halfway. So halfway, at about 250 metres, they are both 7.5. There we go. Forgotten how to draw. At 250 metres, the dew point and the air temperature are both 7.5. It's at this point that you get a cloud forming on the way up to the mountain. So the cloud bottom is 250 metres. And it goes up to that inversion where all of a sudden the air gets dry. As the air continues to climb over the mountain, the bottom of the cloud runs over the mountain, is forced to rise and releases its moisture with drizzle and hill fog and so on. So it loses some of that moisture. But you've still got a lot of cloud over the mountain. At the same time, the top of this cloud, this bit, is forced, because this whole chunk gets moved up, not just the surface, all of the air gets shoved up. The top of the cloud is forced into the dry air above. Then, when you remove the hill again on the other side, because you've got high pressure, the air is generally sinking above the inversion, all of it sinks back down again. It's like jelly. Push some jelly and it wobbles. It doesn't stay in the same place that you pushed it. It wobbles back because jelly is very stable. It's the same with this kind of weather setup where you've got high pressure. If you force it up, then eventually when the obstacle gets out of the way, it comes back down again. As the bottom of the cloud reaches the top of the mountain, it's continuing to cool. It's about 6 degrees or 6.25 degrees by this stage, both in terms of air temperature and dew point. But as the surface of the cloud comes back down again, it warms up at the rate of the dry adiabatic lapse rate, the dry air, because it's lost a lot of that moisture. So it's started its ascent over the mountain at a slower rate of cooling because it's saturated, and then it begins its descent on the other side of the mountain at a faster rate of cooling because it's no longer saturated. So the dew point stays roughly the same. It probably goes up to about 7, but it's going down 500 metres. That means it warms by 5 degrees. The air temperature at the bottom ends up about 11.5. So it's a modest rise in temperature from 10 degrees to 11.5. That's the Foehn effect. It's also drier. So the cloud at the bottom of the cloud has dried out. But at the same time, this drier air up here is mixing with the top of the cloud and then forced back down again. So not only have you got the air dumping a lot of its moisture over the hill and coming back down the other side, warmer and drier, but you've got all this dry air up here mixing now with the slice of atmosphere that was forced above the inversion. And in fact, this continues to oscillate because it normally overshoots. So when it's forced back down the other side of the mountain, it normally overshoots and then it rebounds back up again. Again, like poking a jelly, it wobbles. It doesn't just go one way and back again, it continues to wobble. And that wobbling will take the air back up into the dry bit once again, less so, but still a little bit back up into the dry bit. And so you've got this continued mixing then, which you didn't have before the air climbed the mountain, because this air here was so stable, it was slowly sinking, and this air didn't have enough buoyancy to push itself into the dry air above until it was forced to rise over the mountain, and that caused it to mix with the drier air above and to dump a lot of its moisture over the hills. So for those two reasons, the air on the other side of the mountain is a lot drier and it's generally cloud-free. So that, hopefully, explains the Foehn effect, why you have clear skies and higher temperatures on the other side of the mountain range. Of course, 500 metres is a relatively modest height. In other parts of the world, the Alps, the Rockies and so on, much greater mountain ranges, and you can have much higher extremes of temperature rise and so on, and some remarkable extremes like temperature going from -20 up to +10 degrees, and there's a well-known name for the Foehn effect in North America, the Chinook, and it is also colloquially named the snow eater because, of course, it can, when you get the change in wind direction and this warm Foehn effect coming down a mountain, it can eat the snow, it can melt the snow very, very quickly. Happens in the Alps as well. And in the summer, it can cause bursts of heat and wildfires as well. So it can be quite a dangerous wind. In the UK, not so dangerous. The extremes that you get out of it aren't quite as wild, but it has led to some extreme temperatures. The November temperature record was set in Ceredigion in West Wales. That was a Foehn effect wind that resulted from the wind going over the Welsh mountains, and also Southerland, Achfari, in December and in January, both months, that location in Sutherland, northern Scotland, set the UK maximum temperature record. Again, Foehn effect wind. So, of course, in those months of the year, November, December, January, the sun is so weak in the UK then it needs a bit of assistance from the Foehn effect. In other parts of the year, or in other times of the year, that's not necessarily the case. Just going back to this and this. As I mentioned, this area of high pressure, you've got sinking air throughout it, apart from in the lowest 1,000 metres or so, and it's within this air where you've got this layer of cloud. That layer of cloud is sticking around in November because the sun isn't strong enough at this time of year to heat up the air at the bottom and give it enough buoyancy to push the cloud up into the drier air above and then lead to sunny skies and even more heating. And I think I worked out that the temperature at the moment, if the sun was strong enough to lift that low cloud into the dry air above and continue heating, several hours of heating through the day, then you'd end up with mid to high 20s in this kind of weather situation if the sun was stronger, if it was the kind of strength you get in July, August and so on. As it is, it's November, you get only a limited amount of solar heating through the day, not enough to lift, to give enough buoyancy to lift that low cloud into the drier air above and lead to clear skies. That's why you basically need to force it up, and the only way that the weather manages to do that is to push it over mountains. And in northern Scotland, of course, you have got mountains to push over, as I mentioned. Just taking a look at this again on Wednesday. And let's remove that. This highlights some of those mountain ranges I was talking about. The coloured in area here is everywhere above 500 metres. So that's why I chose 500 metres. Quite extensive areas across central Scotland through the Grampians and the Highlands where the land is above 500 metres. So you can imagine air that's moving from Stirling to Braemar to Lossiemouth, starting off cloudy, ending up drizzly and low over Braemar, and then ending up clear over Lossiemouth. You don't have to take my word for it. I've got a nice little diagram that shows it here. This is another one of those tephigrams, so another one of those vertical profiles of the atmosphere. This one in particular is for Stirling, okay? And it shows the predicted vertical profile. So this isn't taking a weather balloon, this is predicting what a weather balloon would experience if it was flying from Stirling up through the atmosphere on Wednesday afternoon. Wednesday's a great example because you've got southerly winds across Scotland, you've got relatively moist air, and you've got a marked Foehn effect because you've got higher pressure, this descending air through here. So it's a similar sort of look to the diagram I showed before of the actual vertical profile across northern England. This is Stirling, and what you can see, the two lines, the dew point and the air temperature, very far apart, above 1,000 metres. So dry air up here, but then in the lowest 1,000 metres, they're right next to each other. So you've got that thick cloud, that thick low stratus for Stirling. Now pay attention to this bit here, and I'm going to flick on to what it looks like for Braemar. So it's the same thing, but it's showing Braemar at the same time. What you can see is it went up a bit because Braemar is 335 metres, Stirling's 26 metres above sea level. So Stirling starts off close to sea level. Then the air, as it moves over those mountains, it's forced up. Braemar's 335, as you can see, the lowest part jumps up. You've still got those lines close together. In fact, you've just got hill fog, maybe some drizzle for Braemar. And then you've still got this area not far above Braemar, a few hundred metres, where it's clear skies. So if you were to, shoot up a weather balloon or show a drone up through the atmosphere in Braemar, you'd have cloudless skies just a few hundred metres above, but very dreary conditions for Braemar itself. Then, as that air descends on the other side, watch this change take place in these bits here. This is Lossiemouth, same time. Lossiemouth's at a lower height, it's virtually sea level, so again these lines come back down again. But what happens is that they're quite far apart at the surface. You've lost that low cloud. But at the same time, the dew point rises above that. In fact, there's not really evidence for an inversion above Lossiemouth. The two lines are virtually parallel as they go up. So just skipping back to Braemar, these lines very far apart at about 3,000 metres, for example. They're much closer together at 3,000 metres. The opposite happens close to the surface. Braemar, Lossiemouth. Braemar, Lossiemouth. And it's almost as if, you can imagine, all this area, air in this part of the atmosphere, the lowest 5 kilometres or whatever, just mixes together like that. So the really dry and much warmer air above the clouds mixes with the cloudy area for Lossiemouth to result in generally clear skies and warmer air at the surface, but also higher up as well. Hope that makes sense. Probably quite a long rambling explanation of the Foehn effect, but it is the deep dive after all. Right, quick look at the rest of this week. There isn't much to talk about, I'll be honest, and it is all about those areas of cloud and cloud breaks, effectively. As I mentioned, rest of Tuesday, some drizzly showers for western parts of the UK, mostly hills and coasts, but otherwise a mostly fine bonfire night for many places. Any cloud breaks are likely to fill in with fog, although northeast Scotland, again, possibly seeing some decent cloud breaks developing through Tuesday and continuing into Wednesday morning. So that's where the lowest temperatures will be first thing Wednesday. Otherwise, it's a very mild start to the day. Temperatures of, 12, 13, 14 Celsius. It's more of the same, really, through Wednesday. A chance of some cloud breaks there for North Wales, parts of northern England. Same mechanism as northern Scotland, Foehn effect, but yeah, they'll come and go. I don't think they're going to be as reliable, perhaps, as parts of northern Scotland. Over on the left here, we've got the jet stream just coming into view, some weather fronts waiting out in the Atlantic to come in, and the isobar's tightening. So later Wednesday and into Thursday, the winds strengthen. This is a southerly wind, so it does mean it's going to be very mild over the next few days. We had some colder air with us over the weekend at the start of this week. But overnight temperatures remarkably above average, actually, both by day and night, double figures generally. Once again, northern Scotland seeing some decent sunshine on Thursday. Otherwise, most of the UK again under low clouds, some drizzle in the west and some strong winds. Perhaps 40, 45 miles an hour across western Scotland, so blustery in the west. And we're likely to see some thicker cloud and some outbreaks of rain turning up with this weather front. It's just trying to move in from the Atlantic and coming up against the high pressure, so weakening. And that nevertheless will bring some damp weather to parts of Northern Ireland and western Scotland during later Thursday and into Friday. But again, some cloud breaks there for northern Scotland. Hit and miss cloud breaks elsewhere. You wouldn't rule out cloud breaks just about anywhere because you could have some patches of drier air originating over the continent and drifting north into southern parts of the UK over the next few days. They're not going to be that reliable though. They'll come and go. Friday, you can see some rain edging into the southwest, and the weekend sees a front crossing the country. This is Saturday, and bringing some showery rain. No huge totals, certainly, and with all the dry air at the moment, nothing to be too concerned about. But yeah, some showery rain crossing the country on Saturday, west to east. However, behind that front later Saturday, a better chance of some sunshine breaking out for western parts of Britain. Then another front comes along, and this is likely to bring some wetter weather once again into northwestern parts of the UK, basically as we start off Sunday. And that's going to cross the country. This is a more active area of low pressure, actually. I'll show you it on the bigger picture. Here it is. It's being picked up by the jet stream. And it's moving in. A little bit of uncertainty at the moment on the track and the depth of that low as it arrives. It's going to swing to the north of the UK because we're still going to have the jet stream directing systems to the north of the UK, but it's likely to bring some strong winds to the northwest, so for western Scotland and for Northern Ireland, and some outbreaks of rain. The general theme is that the front as it crosses the UK will weaken, likely to bring some cloud and some showery rain for a time on Sunday. But once it clears through, watch this, high pressure returns. However, this high pressure comes in from the Atlantic behind the cold front. Some uncertainty about this, but that means there's a good chance that it will build into clearer air. What does that mean? A better chance of some sunshine at the start of next week. This is the most likely weather pattern for Monday the 11th of October. It's got high pressure to the southwest of the UK, dominating things across the country, just some patchy rain for the northwest of Scotland. But with that high building in after a cold front's cleared, there is the good chance for some clearer spells, some sunshine with the high pressure at the start of next week. A bit of uncertainty, though, about the clearance of the front, so it's not guaranteed that the front will completely clear and that we'll be completely free of the cloud associated with that front that goes through on Sunday. Either way, once we've got high pressure at the start of next week, it's likely to stick around once again throughout next week. High confidence on this, high pressure sticking around for another period of time. This is Wednesday, this is Saturday. Now, as the week progresses, it looks increasingly likely that more cloud will be mixed in with the high. So even if it starts off sunny, well, there's an increased chance later in the week that that low cloud will return because it will just start to rotate around the area of high pressure. It will suck itself in from the Atlantic, for example, as the week progresses. This is Saturday, and this is when there are some hints that some subtle changes might start to take place. This is the most likely weather pattern for Saturday, high pressure still nearby. This is the second most likely weather pattern, high pressure to the south, but weather fronts starting to move into the north. So wet weather starting to arrive into the north and northwest of Scotland. So next week, if we start off with clear spells, chance of frost and fog at night, but then increasingly cloudy again, so mostly mild, most of the kinds of temperatures that we're seeing this week, 9, 10, 11, 12 and so on. However, around the middle of the week, and this has been signalled for a while, 17th, 18th, 19th of November, these systems are likely to start to increasingly affect the UK. And this is shown quite clearly actually from the European model pressure anomalies. And this is the summary for next week. So this is the average pressure anomaly throughout next week. High pressure, slap bang over the UK. But fast forward another week, and this is the middle of November, and it's got higher pressure to the south of the UK, so the driest weather most likely hanging on to the south, with systems starting to come into the north. So if it turns unsettled through the middle of the month, it's most likely to start to turn unsettled from the north. And just a final graphic here to show that in a different way. This is the next 2 weeks of weather patterns illustrated by various colours here. Blues typically mean low pressure. Now, it's got this light blue for the last few days. That's kind of because the high pressure that's been dominating things has been quite far to the east, and we've had this southerly airflow with low pressure to the west. But effectively, we've had high pressure influencing our weather for the last week. And these reds and oranges indicate that's going to continue for the next week or so. But these blues, which indicate lower pressure most likely dominating, start to take charge around the middle of the month, but uncertainty about exactly when and how that takes place. We will, of course, keep you updated right here at the Met Office. Please do stay tuned for all those updates. And don't forget, the Weather Studio Live is back this Friday, 12:15. So I hope to see you there. Bye-bye.